Now, I'd like to welcome our presenter today from the University of Wisconsin-Madison, Dan Negrut.
Thank you, Jacob. Thank everybody. Can you hear me, Jacob?
Yep, you sound loud and
Good.
clear.
Okay. Thank you so much for the introduction. Good afternoon, everybody. So the title of the presentation, I hope that you see it on your screen, developing an open source multi-agent simulation environment for connected autonomous vehicles. So this was a 1-year project which we finished on May 31st, and now we are on to a second year project, which is slightly different, and I'll talk about it at the end of the presentation. I just want to start with some acknowledgements. So this work was done under a 1-year project. Um, People involved in this project, undergrad student Dylan Hatch, he graduated in May and moved on, was hired by Google. Asher Elmquist, he's still here with us in the lab working on his PhD, and Radu Serban, who is basically the person in charge of the software architecture of Chrono and was involved in this project as well. I want to dive in and just, on one slide, tell you a couple of things about some equations that underpin this infrastructure. So the bottom line is that what we're doing in the lab is simulating multi-dynamic systems. It so happens that vehicles are such systems, and we have like a bunch of equations that we're solving. They're listed here. I'm not going to get in details, but long story short, solving these equations gives you information about the time evolution of mechanical systems, in particular vehicles. Here is such an example of a mechanical system. As I said, it doesn't have to be a car. It can be anything that has multiple bodies that interact with each other through friction contact, or they're like moving, or they are moving under the effect of external forces. Um, I showed you some equations. I'll show you a simulation. Um, those equations basically provide the foundation for a simulation uh, platform, which is called Chrono. This is a joint project with a collaborator from Italy. And the name of the software is Chrono. It is a physics-based simulation engine, multi-purpose. Um, it is open source, released under permissive BSD3 license. In other words, anybody can use it, modify it, uh, sell it if they care to do that, and so on. It provides support for modern multi-dynamics. Specifically, you can simulate the time evolution of flexible body systems, and also there is support for fluid soil interaction problems. And at the right of the slide, I provided some information where you can learn more about this project in case you are interested in this simulation platform. Um, the, the software is what we call middleware. In other words, it is designed from ground up to be embedded in third-party applications. So in other words, you own the main program and you call Chrono for simulating components that you care about. It's modular. There are many modules to it, and you don't have to use all of them unless you need a specific set of tools in your simulation. Is expandable. It's built on using C++. It runs on multiple platforms: Windows, Linux, OS X. Uh, you can compile with multiple compilers. Some of them are listed there: CL, the Visual Studio compiler, GCC, Intel compiler, Clang. And then it runs on multiple architectures such as x86 if you want to run it on Intel or AMD chips, ARM if you want to run it on platforms such as Jetson, or and Power 9 if you want to run it on IBM chips. Beyond strictly multi-dynamics, I mentioned that we do fluid soil interaction. These are the equations of motion. This is basically, this slide is the analog of like the slide that we saw 5 slides ago. Um, the first equation is the mass continuity. The second one is the momentum balance, also known as Navier-Stokes. Here we assume that we work with an incompressible Newtonian fluid. We solve this problem, these equations in the framework of the smoothed particle hydrodynamics method. And on this slide, I'm showing a example application of affording of a vehicle. This is something that is tied to or inspired by some project that we have ongoing with the US Army. Uh, One slide about the structure of Chrono. So Chrono is built to leverage to the maximum extent possible parallel computing. We do so by leveraging multi-core chips, the GPU in some cases, and sometimes we use MPI to engage in one simulation multiple nodes. Um, on this hardware infrastructure uh, rests a set of core modules or blocks, and one of these blocks provides support for equation formulation in the code. Another one solves, another block is aimed at solving these equations. We have support for collision detection, high performance computing support, and pre and post processing. So there are some discipline oriented modules that build off this abstract foundation. Specifically, we can solve multi-body dynamics problems, finite element. I told you about flexible bodies, nonlinear finite element, where the nonlinearities come from like three sources, like nonlinear material, nonlinear boundary conditions, and nonlinear, like large deformations. Um, Beyond that, there's support for fluid interaction, as I showed a couple of slides ago, and we are building on top of it. Uh, I'll briefly mention about another module that is is under development. It has to do with sensing. Um, there is an interface that the user communicates with the solver through. So rather than having like very low level or requiring very low level access into the guts of Chrono, there is an API that allows you to set up a model, to take one time step, to show assets on the screen, and so on. This entire setup is meant to run either in parallel on one um, workstation, or it can employ multiple nodes in a distributed fashion. As I said previously, this is supported through MPI. Then, if you have an advanced Chrono user, he or she can use this interface to set up models, but sometimes for certain applications, we have support, like modeling support, pre-canned. For instance, if you know that you want to model a vehicle, then there are templates that help one set up a model more quickly. And I'm going to talk about this a little bit later. Um, so actually, I'm talking about right now about Chrono Vehicle. Um, I already mentioned these. There are two ways to go about setting up a model in Chrono. One is the hardware, where if you're an advanced user, you can put together a model piece by piece. It's just like building a house brick by brick. Or you can take a template-based approach where Radu put together templates for suspension, for the driveline subsystem, and so on, the steering system, so that you can very quickly set up a model and get going very quickly. Um, the advantage of that, beyond being able to run a model very quickly or soon after you pick up Chrono, is the fact that having this template-based approach prevents you from making all sorts of mistakes that usually crop up when you start from scratch and you get down to modeling a suspension piece by piece. This Chrono vehicle concept is, as I said, a templates-based approach that we embraced. It's flexible. We use parameterized templates. You can modify them, and it's expandable because it draws on a C++ inheritance mechanism. You can take, for instance, an existing template and augment it, or if you want, you can put together a completely new template that perhaps user in your group will benefit from. Here is an example on slide 11 of a double wishbone suspension template, and I'm not going to get into details, but it has all the components that you'd expect to encounter when you deal in a vehicle model with a double wishbone suspension. There are hot points that you can move around. There's an option to mirror uh, one suspension to the other side of the vehicle, and so on. Looking beyond suspension, there are several subsystems that are abstracted when handling vehicle dynamics in Chrono. So there's a driver component, there's a powertrain, terrain, tires, and a chassis. And this slide shows the information flow that exists between these subcomponents. And on the left, you see the specific implementations that are associated with these sub-models. Let's say, for instance, let's take the tire model or the tire system. We have like a rigid tire, support for Negrut tire, Pacheca, Fiala, and FEA based, and so on. For terrain, there's like rigid and deformable, and then you get into powertrain, driver model, and so on. And these vehicles, they you can, and components of the vehicles, you can run them um, in a fully coupled fashion, or I'm not going to get into details here, but you can take a vehicle, split it into pieces, and use some sort of co-simulation, for instance, to simulate the terrain on one node, the vehicle on a different node, the four tires, the vehicle meaning the chassis on a different node, and the four tires, for instance, on four other computers. Um, we're interested in like handling geometry accurately. So in other words, a vehicle for us is not simply like a point mass that has a certain mass and perhaps some mass moment of inertia associated with it, but it has a geometry and it can interact with the surrounding environment. In terms of like the performance of this, by the way, this is, I hope that this comes through. This is a simulation of a Humvee model. And in terms of performance on the left here, this is for 20 seconds of simulation. We show the simulation runtime when the simulation is run with 1 millisecond. And on almost all platforms, except on a Windows laptop, this runs real time. And this is for 1 millisecond. In reality, you can run this simulation at 3 milliseconds and run it stably as well. So long story short, the simulation, as far as vehicles are concerned, is real time. The question um, is this high fidelity vehicle with suspension models and driveline and so on, is it actually accurate? Does it pay to have complexity? Does it uh, provide any accuracy at the level that you'd expect from a high fidelity model? And to that end, to answer that question, we went through some validation processes. We did validation whenever possible at the component level. For instance, we validated against atoms, the subcomponent, the multi-body dynamics component. We look at tires, and University of Iowa, um, uh, we had a collaborator there, Professor Sujiyama. He helped with the tire model validation, and we have other validations for fluid flow interaction and so on. But then moving on, we have like a subsystem level validation and then a system level validation. And I'm going to spend probably like 3 minutes talking about the system level validation. We did it through a NATO benchmark uh, uh, test that we participated, or a process that we participated in, and the validation was both for wheeled and tracked vehicles. And here, what I'm showing is like for tracked vehicles. I'm not going to get into details, but there was like a double lane change maneuver that we validated against. There was a maneuver in which the vehicle was supposed to operate on a side slope and try to negotiate on deformable terrain an obstacle. And the question was like, how fast can you move before you spin out of control? Then there was like another benchmark to simulate a step negotiation, if you can climb a step. And then was another one had to do with um, determining the 2.5 G ride limit speed. How fast can you go over over certain obstacles of certain heights and not subject driver at an acceleration higher than 2.5 g. So with that out of the way, this is the vehicle part. And we build on top of that an infrastructure which we call Synchrono. And the idea is to simulate everything beyond just vehicle dynamics, to simulate sensing and simulate communication and simulate virtual environments. They want to do it in a scalable way uh, that supports a heterogeneous ecosystem. So at the end of the day, we would like to have uh, conventional vehicles, like driven by, for instance, a student in the lab, operate in the in the same ecosystem with a vehicle that is autonomous, and it can be on road or off road. So to cut it to the chase, this is a simulation of an intersection in Madison, is Park Street and University Avenue, and in this framework, we have like 30 vehicles. They don't have any drivers. All of them are autonomous. And there's a traffic light. I don't know if you can see it. I'm moving my mouse. There's a traffic light here and there's a traffic light there. And the idea is that these vehicles, because they have LiDAR sensing and they communicate with the traffic light, they can coordinate their motion so that they avoid any crash. And the idea is for the vehicle to talk with the traffic light through DSRC messages and use GPS IMU information to maintain path along the road. On the next slide, um, there is a zoom-in simulation or rendering of the same simulation. And you can see here the traffic light. I don't know if you can see my mouse, but uh, this is more like a street level of the same simulation. And you can see the vehicles evolving uh, without any driver model stopping if the vehicle in front of them stop, so that there's no crashing and the vehicles maintain a certain distance between each other. A couple of things about how this synchronous infrastructure is meant to work. So we have this simulation layer, which essentially is like, for all purposes, is like Chrono. And we can simulate, for instance, a rover, we can simulate a vehicle, we can simulate sensing, we can simulate environment, virtual environments. But the idea is that this is the simulation component, and on top of that, we have a virtualization layer. For each vehicle, which we can call agent, we have a software counterpart, which essentially talks to what we call the Synchrono Daemon. And basically, this Synchrono Daemon is responsible for maintaining time and space coherence between all the agents participating in a simulation. So on this slide, before I move on, I want to say that when it comes to agents, agents are like entities in a simulation that have a brain, so to speak, or a piloting control program. This is this is what brings autonomy to that agent. And then we have like virtual world static element at the right of the figure, VW static element. These are elements, for instance, you can think of it like, for instance, uh, uh, a leaf that is blown by wind. It doesn't have brain, it moves, or you can think about it as a car driven by a student through a joystick. It moves, it has its own dynamics, but its behavior it's not basically self-determined through like a piloting control program. So you have a combination of agents and these virtual elements, and they communicate to each other, and their coherence in space and time is maintained through this synchrono daemon. And I'm going to get into details here. I already told you that each agent, like this agent corresponds to like a rover that moves in an autonomous fashion. And you have these virtual world static or dynamic elements, if you like, buildings, trees, and so on, that can be sensed in the virtual world. And again, the synchronous daemon maintains the coherence of this environment in space and time. And I'll talk shortly about that concept. So when it comes to Synchrono, this has a server-centric design, and there are like two servers. One has to do with the dynamics, and one has to do with the communication. The implementation of this is realized through message passing, and we have like a UDP communication layer that we build on, and we use Google protocol buffers in Synchrono. And in terms of like maintaining time coherence between multiple agents participating in one synchronous simulation, I just want to start here with the time evolution of one agent. Imagine that this is a car, and let me just provide a little bit more backdrop here. Imagine that you have like 30 vehicles, and you have like 30 nodes that participate in this simulation, and one vehicle is run by one node. So obviously, you can have an agent that moves at a certain pace in time on one node. Let's say that it has a very fast chip, while another vehicle runs on a different node that has a very old processor, and therefore its simulation um, happens at a slower rate. And what you are concerned about is maintaining a time coherent environment for the simulation of all these agents, no matter what hardware they run on, or how sophisticated, how complex the agents are, their physics is. So you have one physics that moves on one timeline, and then you have another one, and as you can see here, perhaps in green, you have a second agent that moves at different time steps, and the idea is that you want to have the same time perceived by the two agents because they have to sense each other, and perhaps, for instance, if they collide with each other, they have, you cannot miss that event. You don't want to move forward into the future while another one is lagging behind in the past. And this synchronization is enforced by what we call a simulation heartbeat. And if one simulation on one node for one vehicle happens very fast, that simulation, that node needs to slow down and basically spin in place until the slower agent catches up and they maintain this time coherence. And I'm not going to get into details, but that's basically the gist of it. And this is essentially what the Synchrono Dynamics Server accomplishes. What the communication server accomplishes, I'll talk about that in like probably like 2 or 3 minutes. So what I discuss about uh, thus far is like the Synchrono setup and how the physics is simulating and how time coherence is informed. But there are a couple other things that are important in this equation. You need to have virtual worlds, you need to simulate sensing, and you need to simulate connectivity. So I have 7 minutes to talk about these three things. I'm going to move very quickly through them. In terms of like virtual worlds, this is an airplane picture of that street, that intersection, sorry, Park Street with University Avenue. So this is what was taken from a Cessna flying above that part of Madison. And on this slide is a mesh that was generated based on that information. And this mesh with texture and such is what is the input for Synchrono. And this is where we exercise our sensors in this virtual world, and these are the buildings and the trees and other assets that come into play when we have sensors on a vehicle and we pick up cues in relation to how a vehicle looks, how far it is, and so on. So here is a simulation of the sensing that we currently have, and this is a demonstration of a vehicle that has 6 cameras and 5 lidars and 1 GPS and one IMU system. And on this slide, you can see how the vehicle drives in Chrono, and it senses through all these channels, the cameras and the lidars, how it senses the world around it. And in the left corner, you have the IMU simulator, and then next to it, you have the GPS simulator. Left lower corner, you have the lidar simulator, and then you have cameras, and there's like a third-person view of the ego vehicle here. But that's essentially where things stand right now in terms of like simulating sensing. This is what the sensors pick out of that virtual world that was generated by a plane flying over that street. So sensor simulation right now what we simulate is the IMU, GPS, camera, and LiDAR. Perhaps looking ahead, we might be interested in infrared and radar, although these are not pressing. They're not on our radar, so to speak, right now. Um, I didn't say anything about the communication, but I mentioned that there is a communication server, and this is in place to simulate to fake communication. And this communication can be vehicle to vehicle, or it can be vehicle to infrastructure, and so on. And I'm not going to get into details here, but right now we have some preliminary support for map messages and SPAT messages, and we look at two intersections, although we kind of like abandoned this line of work because the student graduated and moved on. But we were looking at an intersection in Peoria because we had information about that, and the same intersection in Madison that I just showed at the intersection between Park and University Avenue. So how is this useful? Uh, Obviously, it's useful to test driver models for autonomous vehicles because it's safe and quick and comprehensive. We can do pretty crazy stuff if you have a virtual environment because it's safe and it's fairly inexpensive once you set it up properly and it's predictive. Um, Another thing that is very attractive is that you can use simulation to generate synthetic data for machine learning. And the highlight here is that you can label data because you know all the assets in the simulation. So if you use supervised machine learning, this comes very handy. And finally, uh, we are about to start using these in an artificial intelligence pipeline. So imagine that you want to develop a driver model for an autonomous vehicle, and you need uh, to to gauge the quality of your image segmentation or image recognition or your SLAM algorithm. So all these, you don't need to go out there and get the data in the real world. You can generate it synthetically and do your SLAM and understand if your algorithm works well enough or not. So there's a bunch of research questions that you can envision addressing with this with a tool like this. Um, for instance, one research question that is extremely important. Um, how can one simulate senses accurately? We're looking into that. How much accuracy do we need? Uh, how can how do we know that, for instance, if you develop a driver model in general, how do we know that that's going to work in the real world? This translational attribute of it is not that clear, and this is a very important question. Um, how should you generate virtual worlds? Um, how can you fuse simulation data and actual data to benefit the task of deriving AV driver models and looking beyond autonomous vehicles? Certainly, there's an opportunity to use something like this in robotics. So looking ahead, we have we just started essentially 2 weeks ago, year two, where we focus on sensing simulation is critical in our infrastructure. Um, we have some two undergraduate students looking into um, scaling up, improving the scalability of Synchrono so that we can have hundreds of vehicles participate in one scenario in real time. And then we're interested in better ways of creating and managing virtual assets. In other words, to generate the virtual environments worlds. But here, most likely, we're going to reach out and work with other partners so that we don't reinvent the wheel. So it's 2:29. I think that gives us 1 minute for questions and answers, or I don't know, at my end, I can stay as long as needed. But I know that I had 30 minutes and it's 2:29 now. So thank you very much for your attention. Thank you for participating in this. And I look forward to answering any questions that you might have.
Thank you, Dan. We do have a participant typing right now, so I can read that out loud once we get that in. But thank you for the presentation.
Absolutely. And do people have to type or can they just ask directly?
Uh, Unfortunately, the participants don't have microphone
I
access,
see.
so typing will work. what's the benefits of this simulation comparing to others like Gazebo?
Right. So I think that we have way richer physics than what you have in Gazebo, uh, and the software stack is oriented towards vehicle dynamics. Um, and if you look at Gazebo, I know that they have simulation provided by, for instance, Bullet, and there are a couple of other Mujoku and such. But by and large, they were set up to run, or their target application was robotics. Well, in our case, it was a long process of developing vehicle models, validating them, making available um, more sophisticated tire models, and so. So that's one attribute that I think that it sets this aside. Another one, for instance, we were working on um, um, supporting communication, which I don't know if it's available in Gazebo. Secondly, we look at the sensor models that are available in Gazebo, and we found them to be extremely um, basic. For instance, simulating LiDAR information. The models that Asher is working on are way more sophisticated than what's available in Gazebo. So those are some of the advantages. Um, on the other hand, I must say that a lot of people know about Gazebo, and not that many know about us. So there are people who made an investment in Gazebo, and probably they're familiar with it and they find it useful. If that's the case, then I think they should stick with it. But we hope to bring a fresh perspective to this idea of autonomous vehicle simulation through the work that we're doing. I don't know if I answered the question.
We do have some more people typing, and it looks like that did answer the question. So thank you for that,
And by the
Dan.
way,
Next,
just quick, just a follow up. If anyone after this is over realizes, oh, I should have asked that question, please email me, and I'll do my best to answer it. If not, I'll ask Radu or Asher to help. But please reach out. We'll be more than happy to get back with you.
and to add to that, I will send out a recording of this email with the link to the slides that Dan already provided. So I can also include Dan on that email as well. So his email will be right
Great.
there. Definitely want to encourage that collaboration and reaching out. But Dan, we did have another question come in. Is it possible to develop your own worlds within this simulator? How easy is it to create traffic scenarios, lane change, exit highway,
Right.
etc.?
So here, so we haven't done that, but I can tell you what we have done and where we're heading in that direction. I don't know if you're familiar with this Vector Zero company. We just found out about it recently. But I reached out and they supposedly are kind of like the big player in this segment. And we're going to look very closely into doing exactly that. There was a slide where I said that we don't want to reinvent the wheel when it comes to virtual worlds. That's what I meant by that. There's this company, Vector Zero. They they are really good and they provide standard definitions. Like there is a certain format that we're going to try to work with. But at the end of the day, long story short, anyone who has a mesh, essentially, that's how we import right now virtual assets. Like virtual world to us is just like a mesh that we are sensing. Long story short. But moving forward, we want to open up the possibility of having someone use an asset that comes out of vector zero and leverage it in Chrono. Now, I have to clarify that, and you know, in the interest of full disclosure, I do not want to say that after 1 year, this project is something that you can just download and install. You can install Chrono, for instance, and there are installers for that and such. But Synchrono and this infrastructure is very much work in progress. It's like 1 year old, and essentially there was support for one student. So we're very committed to this. We're very excited to work with it. Actually, we're using it in the lab ourselves, and we're super excited to pursue collaborations. But right now, it is what it is after a 1 year project, which paid one student. I hope that I answered the question.
All right. Well, I want to thank you again, Dan, for the excellent presentation and thank everyone else for joining on. As we mentioned, I will send out the recording of this. That should be by the end of the week. So when you receive that, feel free to follow up with Dan on any questions that you might have.
Yep. Thank you,
Uh,
everybody. Really appreciate it. And thank you, Jacob.
Perfect. Well, everyone have a nice day. We'll see you at the next one.
Bye. Bye.